watching. Let's
Go ahead.
go ahead.
And next, we will study principle of impulse and momentum. Again, this is similar. What we studied in last week. The topic of work and energy. We have a principle of work and energy. Here we have a principle of impulse and momentum. Principle of impulse and momentum. We also studied in particle dynamics. They are quite similar. The only difference is in particle dynamics. It's about particle. A rigid body. But in a rigid body dynamics.
A rigid body dynamics.
It's about a rigid body. So, as mentioned, this impulse and the momentum method, for example, impulse and momentum, this method is actually a direct solution to problems involving velocity and time. And you know, if a problem involving force and time, it should be able to be solved using kinetic equation of motion plus kinematics. Oh, I have got a touching here. Okay, can you explain why we get a different force? Oh, okay. You asked why. Actually, no reason. Just that's the nature of angular momentum. And if you select different points for your calculation of angular momentum, you will have different magnitude. Okay. This is different from kinetic energy of a region. It has only one magnitude. It doesn't matter which point for your calculation. Okay. I hope you can understand this. That's the nature of angular momentum. Okay, so continue what I mentioned just now. And the principle of impulse and momentum is direct solution to problems involving force, velocity, and time. And actually, for quite a lot of problems, if in that problem, you know how long exactly the time duration, then that problem can also be solved using kinetic equation of motion plus kinematics. And you know force, and you can find the relationship between force and acceleration. And then if you know acceleration, you can work out the velocity. Okay. After a certain time duration. So that's just one case. But in some other problems, the time duration cannot be measured. So for example, impact problem. Impact very quickly in a very short time period. And normally you don't know the exact time duration of impact. For that kind of problem, if you don't know the exact time duration of impact, you won't be able to use kinetic equation of motion plus kinematics to solve that. And for that kind of problem, impulse and momentum should be the only solution. And we will talk about this in the second part. Okay. Now, what is principle of impulse and momentum? There are two principles.
There are two principles.
Linear impulse,
linear impulse
and momentum.
and
And another one is angular impulse.
Angular impulse and momentum.
And we can apply
these two principles separate.
Now, that's the
equation
for linear impulse and linear momentum. In this equation here, it tells you the initial linear momentum
of a rigid body
plus
the
impact, the linear impact in a time duration from T1 to T2 on a rigid body. It should be equal to what? Equal to the linear momentum of this rigid body at the final state. So look at the diagram. And here I should introduce a diagram. This is called momentum diagram. In this diagram, you draw an initial momentum diagram, and you can also draw a final momentum diagram, and in the middle, this one here is the impulse diagram. Okay. In momentum diagram, you only indicate the momentum, including linear momentum, and angular momentum. In the impulse diagram, this is basically as similar as free body diagram. The difference here is not just action forces on this rigid body. And you also need to express the impulse. For example, the impulse of F1, impulse of F2, impulse of F3, and the angular impulse generated by upper moment M, and also linear impulse generated by gravitational force. So here you can see for W, it's W times T2 minus T1. But for F1, F2, and the couple moment N, use integrate. Why there is a difference? Why for F1, F2, F3, and the couple moment M, we don't use force or moment directly times T1 minus T2. Why do we need to integrate? What's the reason? Because we have no any problem. For the gravitational force on this rigid body. This one must be constant. Okay. If this force is a constant, there is no problem to use this constant to time the time duration to work out the impact. But for F1, F3, or this couple moment M, we don't know if it's a constant. Then we can just simply use the time duration to work out the impact. But if they are variable, then we have to use integration. Okay? So that's why you can see the difference here. Okay. So in this one here, because at this moment we are talking about principle of linear impulse, so I use this red circle to indicate what we need to pay attention when we calculate
when we
use the principle of linear
impulse.
We only consider linear momentum, linear momentum, and linear impulse generated by external forces.
Also include this one,
but not include
couple moment.
Now, for the principle of angular
impulse and momentum,
the physical meaning
of
this equation
is
similar.
Similar.
For a rigid body,
its initial
angular momentum, the angular impulse acting on this rigid body in the time duration from T1 to T2. It should be equal to the angular momentum of this rigid body
in its final state.
Okay. Now again, we have this diagram.
The
diagram is as simple, but this time, because we are talking about angular impulse and momentum. I use this red circle to indicate angular momentum. Now, for the impulse. For angular impulse, not just this couple moment. Actually, all external forces can generate angular impulse. So this means all will be involved, including F1, F2, F3, and couple moment, and the
gravitation force.
But one thing I should highlight is to apply principle of angular impulse and momentum, you must indicate which point you are going to use for your calculation. Okay? You must find the point for your calculation. This can be the mass standard point. It can probably be another convenient point for your calculation. Okay. Now, let's have a summary. So, we are going to use a principle of linear and angular impulse and momentum to solve some problems. In this class, we will use this principle to solve only one problem. Okay. Now, for the principle of linear impulse and momentum, the calculation must be about the mass center point of the rigid body. Point G for the rigid body. And this one here is the principle of angular impulse and momentum. This can be about the mass center of the G, but it can be about any other point. It can give you convenience. So here, three equations, three scalar calculation equations. The first two for linear impulse and momentum. And the third one is angular impulse. If you have more than one rigid body in a system, then when you use this equation for your calculation, for linear part, just simply use the center of mass of each rigid body your calculation. Then simply add up. But for angular impulse and momentum, all the rigid bodies, the calculation must be about a same point. Okay, now. Here just shows what we can use
we can use
what we can do by using the principle of linear and angular impulse and momentum. So, for example, here, to work out the velocity of a tennis ball after the racket hit, we can use this equation, linear impulse and the momentum principle, and also in Luke and Billup, if we like to calculate the velocity of a ball after impact, you also can use linear impulse and momentum principle. And here, to calculate the effect of the impact by a bird, a plane, you also can use this equation. So here you can see. Of course, a mass of a bird is quite comparing to mass of an airplane. But here, the impact can be very high. Why? Because the velocity. A bird may be very light, not heavy. But if it's velocity relative to the airplane is very high. The effect will be very serious. Okay. Applications. Okay. Here, and you can see a swing bridge. So for this one here, I think it should be good to show you a video. Let's say a video. Not this one. Oh. No one. It should be noise. Okay, so this is a swing bridge. Yeah, have a look. And the swing bridge can open and close. Now, question. For this kind of a bridge, why the mass is not uniformly distributed? Why most mass distributed close to center point? And this is not the only example. And here you can also see some other examples. Okay, here. Can see this is tower bridge. And there are two sections. Can open and close. And this one here is a swing bridge in Darling Harbour. Open and close. So you can always see the mass not uniformly distributed, but close to station axis. This one here is close to the center point. This one here close to the rotation center point. The why? Okay, if you look at this equation, you should be able to understand. Because if you, for this swing bridge, you have more mass distributed close to the rotation center, then that means the MMI of this bridge about the axis going through this rotation center can be reduced. If this IG can be reduced, that means what? To achieve a same velocity increase, velocity change, you will need a short time to get it. If your torque is a constant. Okay. So that's why. This kind of bridge. Because you always like to open and close in short time. So that's why. Mass is not uniformly distributed. And for this equation, it is a principle of angular impulse and moment. Okay, so that's sample. And another example here is the Chappie test. And we watched a video of Chappie test before. And to design this kind of we must make sure the kinetic energy of the pendulum can be fully 100% absorbed by a test specimen sitting at the bottom. But how to make sure this? This can be solved using impulse and momentum method. And impulse and momentum method, you will be able to determine distance from O to G, and from G to this pendulum, and these dimensions are quite important to make sure the kinetic energy can be 100% absorbed by the test sample at the bottom, and then you will be able to assess the impact of the sample. Okay. Now, I will use the principle of impulse and momentum. Simple problem. And have a look here. Okay, here. There is a wheel, and this wheel is rolling without slipping, rolling forward, and the angular velocity actually couple moment. Its direction is clockwise. Okay. And that means finally the angular velocity of this wheel should be clockwise. We can know this by observation. Okay, so this is rolling without a slipping problem. And we already know this wheel starts from red. So that means initially the velocity of the wheel is 0. Okay, the driving force is this couple moments. And we already know KO is the radius of gyration of this wheel, and the target is to work out the velocity of this wheel, angular velocity of this wheel after 6 seconds. So how to solve this problem? Probably you will think kinetic equation of motion plus kinematics. Yes, this is a very simple problem. you can solve this problem
using
kinetic equation of
motion,
and you can work out the acceleration, angular acceleration,
angular acceleration,
and acceleration at point O. And then you can work out the angular velocity of this wave
after 6 seconds
using kinematics. No any problem. And you can try this. And you can work out the solution. But here we are going to use principle of impulse and momentum. And let's see what we can do here. Okay, so diagram. And we will draw impulse momentum diagram.
Okay.
And because this impulse and momentum,
they are vectors.
Here,
so
I need to define coordinate system. Just for convenience, in this one here, I define clockwise as positive rotation direction. Again, the positive z direction inward instead of outward. Okay, now initial
momentum.
Okay, at this point O is also the mass standpoint. We have M V O 1. Okay. And here we have I O omega 1. That's initial angular momentum, initial linear momentum, and by observation, because the couple moment is clockwise, by observation, and we can know omega VO, these two should be positive. And omega 1 and VO1, their direction can be related to each other. Because this one here is the contact point. This should be the I point. Okay? And no slipping. This should be I point. And similar to this,
we can
indicate
a
finer linear momentum. Fine angular momentum. Okay. Now, impulse diagram. For impulse diagram, we will indicate all the external forces as we did when we draw a free body diagram. So here, of course, we have couple moments M, and here we have weight force W, and at this point A, we have reaction force N, and friction force F. But remember, this is impulse diagram, not free body diagram. So we must indicate impact, and this will be T times T and times T. And we know M, W, all this should be a constant.
All this should be
so
a
in
constant.
this one here, I just
simply use
times the time duration without using
integral.
Okay, so that's required impulse momentum and
diagram.
For this diagram. No touching.
No touching.
My solution. Okay. So firstly, you can define general plan motion of this wheel, and because no sleeping at point A, so point A must be the IC point. Okay, we have already drawn the impulse momentum diagram. M 300. KO radius of duration 0.4. We can use this to easily calculate the MMI of this wheel about the negative going 0.0. And T1 is 0 seconds and T2 is 60 seconds. Initially, it was at rest, so omega 1 should be 0, and the VG1 should be 0. Okay, now we can have three equations.
Three equations.
Look, we can have three equations. Okay, for the first two. This should be about the mass standpoint. And O is the mass standpoint. And for the third one, it's about the principle of angular impulse and momentum. Okay, now the question is, which point should we select to apply principle of angular impulse and momentum? Obviously, we can select the mass standpoint, and we also can select A for our calculation. So which one should give us more convenient? Look at point O. If you select point O for your calculation, the moment arm of W and N should be zero. And you should consider friction force F. But if you select point A for your calculation, what will happen? You will see the moment arm of N and W. For all these three external forces, the moment arm must be zero. And you only need to consider the angular impulse MT, isn't it? So definitely, select point A for your calculation. It should be easy. Now, to solve this problem, we will apply these three equations, and we will select point A to calculate the angular momentum. We start from angular impulse and momentum. Because in this one here, the only unknown parameter we are going to work out is omega 2. So we will start from the principle of angular impulse and momentum. For HA, Because initially the wheel was at rest. So definitely
for HA
should be there. For HA2, this can be expressed using the MMI of this wheel about point A times omega 2.
omega 2.
On the left side is MMI of this wheel about point A times initial angular velocity 0. And in the middle, that's angular momentum. Work out angular momentum.
We must know
moment about point A.
How
to calculate. That's it. As mentioned, weight for W, N, for this is 3. The moment arms are 0. So these 3 are 0. You only have
couple
it's a constant 300
Newton meter.
Okay, 300 Newton meter times the time duration 6 seconds. This will give you angular impact. And then you can see you only have one unknown parameter omega 2. And this can be blocked out. Okay, again, omega is
velocity
a vector. So not only magnitude, but also direction should be indicated. So that's the full solution of this problem using principle of angular impulse and momentum. Okay, as mentioned, definitely problem can be solved using kinetic equation of motion plus kinetics. And I suggest you work out the solution by yourself, then compare with it. And I believe you will find for this kind of problem involving force, velocity and time, using principle of impulse and momentum, the solution can be much easier. Okay. In this problem here, because we only need to solve omega 2. Actually, the first two equations based on principle of linear impulse and momentum. These two equations are not useful for us.
Okay.
Any questions? Okay. If you have no questions, we will move to the second part to talk about the conservative of impulse and momentum. And in this first part, we actually have other example problem, but because